Right, so I finished last time with listing 3 problematic issues in this sketch. And well, the first one is that this bold assumption that this linear operator corresponding to the degree 1 part of capital P, or close to it, it might not split over this bold assumption that it splits over H might fail. And well, the remedy is to work instead over H, we work over its algebraic closure. And we work with holes that are minimal over HI instead. Okay, so at least a partial remedy. And the second issue is, well, okay, things might work well over HI, but how do you get back to H? That's not so easy as it might seem. I mean, once you have a solution, PF is 0, a solution F, and PF is 0, and F lies in C, in this C less than infinity with I adjoint. You can, of course, take the real part and the imaginary part of this germ and hope that one of them will generate a Hardy field over H. And well, that's it takes a lot of effort to carry out this IG. And there are complications that are too complicated to mention. Okay, but even if you find an F in this ambient differential ring C less than infinity, which is infinitesimal and is not in H itself, and satisfy your differential equation PF is 0, you still need to show that this F generates a Hardy field over H. Yeah? And that is also not easy. So so eventually we are able to deal with all these issues, and let me make a few remarks on that. Eventually, we are able to deal with 1, 2, 3. Yeah, partial remedies come from well, let me list here one result. First of all, this H, for certain purposes, it's still too small, right? We assume that it is Liouville closed omega 3, contains all the real numbers, and contains the cosine and sine of any bounded element of H. But for certain purposes, it's still too small, but it turns out, but it takes surprising amount of work, that by extending H, it's can arrange that, well, HI is what we call one linearly surjective, which means the following: you can solve any, i.e. every ODE. Well, the simplest kinds of ODE, basically, y prime plus py equals q, dq now in HI, has a solution in H sorry, in HI, and the solution in I. Of course, H itself is linearly surjective since it's Liouville closed, but to go from, but it's a much more tricky affair of to extend H so that this one linear subjectivity holds not just for H but for HI. But it can be done. But I'm not going to say now how. I mean, it's in fact, I don't remember at the moment even the details. I just say it's surprisingly tricky to do that. You would think just things like that are so simple that it shouldn't be a big deal. But okay. Secondly, well, suppose we already know that this is the case. Yeah. Assume HI is one linearly surjective. So we are already reduced to or arranged that H has this property, which is linearly surjective. Then we are really in business in the following sense. Assume our minimal hole that we have been P, which we have H over H. Yeah, we have this minimal hole, and suppose it's in a certain normal form, as is in a certain. It's too complicated to explain, but let me just say it can be. One can always reduce to that case, but that itself takes a lot of work. A certain normal form. Rather, which can be achieved. Okay, then we are really in the best situation. Then, if we then have an F, right, and F in the rest of infinity, Pf is 0, F infinitesimal, Pf is 0. Well, this will guarantee that everything is okay. Then F is Hardian. Then F Hardian over H. Fact HF. Morphic over H to HF. Remember, this is this H field generated by F hat over H. But this is a Hardy field. Yeah, and isomorphism is as ordered differential fields, or as H fields if you prefer. Right. Yeah, so this will automatically also guarantee that F is not in H itself, and so on. So yeah, it will actually guarantee this normal form will guarantee that this F will have to be very close to F hat. The elements in H that approximate, if you get closer to F hat with those elements, they also get closer to F at the same time. Okay, and this is one of our main steps. Well, both of them are our main steps towards the final, well, to finishing this project.
So
yes.
It's H of I that is one linearly surjective. Does this imply that H itself?
Oh yeah, but H is already supposed to be Liouville closed, so H is already one linearly surjective. But it's true that, yeah, it's in general true. If you have any differential fields. And when you join, I think it's true that if you have an algebraic extension of a differential field, this is one linearly closed, and the differential field itself is one linearly closed. You cannot go the other way around. You can certainly, it descends simply using a basis of the vector space of the extension over the base fields. Right. Any other questions?
Just how does this intervene in the point 2, the fact that h of I is it's an assumption of h of I that you are the conclusion of h of
Yeah,
I.
it's I'll come back to that. How it intervenes is not so easy to explain. Yeah, I have swept many things under the rug, of course, and I hope you get the flavor of things. Another remark I want to make is ultimately this will get you to a differentially algebraic extension of any Hardy field, which is what we call D-maximal, which has no further. Oh wait, no. Sorry, which is H closed. In other words, omega free, Liouville closed, Newtonian and Newtonian. Yeah, that is the and therefore elementarily equivalent Transseries. Yeah, but one other thing, if your Hardy field happens to be a C infinity Hardy field, so if your Hardy field happens to be a subfield of this, then the D-algebraic extensions that you construct are also in. And likewise, if they are analytic Hardy fields, then all differentially algebraic extensions that you construct are also in there. So this is so things work in several different settings, not just for ordinary Hardy fields, but also for C infinity Hardy fields and C omega Hardy fields. Okay, so for the rest, okay. Right, so for the rest, today, well, we'll say more about an aspect related to items 2 and 3, or issues for 2 and 3. And it's of it, and the main thing is that it's of interest in its own right. So I think it's reasonable to say something about it. I mean, which we find quite useful in its own right. We'll also see there that a completely different, something that comes from a completely different angle plays a role. So this is about exponential sums. Exponential sums. So this is kind of a new paragraph, a new section. Exponential sums over Hardy fields. Yeah. And okay. And I will start with a result that had, I believe, a lot of follow-up in literature due to Bojanitsa, who was the first who made a connection between Hardy fields and a classical topic called equidistribution mod 1. Namely, for Hardian, if you have a Hardian germ, yeah, in other words, something that that lives in a Hardy field, that lies in a Hardy field, we have the following equivalence. F uniformly distributed, yeah, let me write it here. F uniformly I will say what that means. Distributed of one. Of one. If and only if F dominates F dominates log X. Yeah, F grows faster than any real multiple of log X. Right. Okay, uniformly distributed but one. Well, let me say that this is equivalent to uniformly distributed but one. Maybe I need, yeah, this means, for this, it's equivalent to the following. If you take the integral from 1 over t 0 to t e to the power 2 pi I n f t dt, this goes to 0 as t goes to infinity for every n. For every n. Yeah, here it doesn't make, of course, to make sense of that, you need to take a representative of f. F is for the moment only a germ at plus infinity, but you just take some continuous representative on the whole interval 0 plus infinity. It doesn't, and whether this is the case or not doesn't depend on which representative you take. So this makes perfect sense for every n greater than to 1. Yeah. Of course, for n is 0, that wouldn't be true, but so you can imagine this is some oscillating thing, and right, and basically by sort of the average value of this function, on larger and larger intervals goes to 0. So that means, yeah, this is not exactly the definition of uniformly distributed mod 1, but it's equivalent to it by a theorem of Hermann Weyl. And this is the easiest equivalent way to say what it is. Okay, so that is something that Bojanitsyn did in the 90s, I believe, and it seems to have had considerable follow-up, ergodic theory and so on. But we can also use it. So using also, yeah, let me say, yeah, functions like linear combinations of R1 IT plus Cn e to the power Rn IT are what are called almost periodic. Technical definition that I'm not going to give exactly. So here the R's are the real numbers, and of course each of these terms, e to the power R IT, has a certain period. It's periodic, but they have different periods which may not be commensurable. So it is in general not periodic, but it's almost periodic. It behaves in many ways like something that is periodic. And also uniform limits of functions like that are almost periodic. And so there is also another classical topic in analysis, the theory of almost periodic functions. And combining these two facts about almost periodic functions and Bose-Nelson's theorem, we have the following. Can use this. Can use this. First Bose-Nelson. Nelson. Yes. Following corollary. It's very useful to us, or crucial actually, that energy Hardy fields and phi1 Vn in H such that if you take linear combinations, you never get something that is bounded, except possibly when it's real. So these are the linear combination, real linear combinations. These are the bounded elements of H. This is, yeah, so any linear combination which is bounded must be actually just either must be some real number. Yeah, typically phi1 to phi(n) are all let's say infinite, strictly dominate one, and linearly independent, such that all the non-trivial linear combinations are also infinite. And then, of course, this assumption is automatically satisfied. Okay. But this is a situation that will then for all f1 up to fn in hi, and now we allow the following happens. If you take f1t e to the power I phi1t, if you look at this is, can imagine this is a fast oscillating, well, of course it's a complex imaginary. It runs around the unit circle with infinite speeds, all of these. But then of course we get also multiplied by terms here. So suppose that this goes to 0 as t goes to infinity. It turns out that this can happen only if the f's themselves f1 t 0 right. So this is it's funny because of course all this business about Hardy fields and the connection to O-minimality is about non-oscillation, and this is a result about oscillation. But it turned out to be important. Right. So the only way that such a sum can go to 0 is that the coefficients have to go to 0. Of course, the converse is obvious. If this goes to 0 and this goes to 0, since these terms remain of absolute value 1, then the sum would also go to 0. Right. So now I'm going to explain how this relates to linear ODEs. Or how it relates to what we are interested in. I'll explain. reduce diffuse or over that complex, over that algebraic closure. So H will be linearly closed. And I'm going to assume that H is already sufficiently large. It's linearly closed containing R. And K, I'm going to assume my algebraic closure. I'm going to assume that this is one linearly surjective. That is fairly strong. As I mentioned, part 1.1 there says that we can do that. Can always extend H so that it is true. Yeah, okay, so this is my assumptions on H. Oh yeah, I didn't even say that it's a Hardy field. Okay, yeah, let's see what is E for F written as HI, GH, H. So take a typical element of K, you write it with its real part G and its imaginary part H. And then of course e to the power F is e to the power G and e to the power HI. And so it's, of course, you can write in purely real terms as cosine G plus cosine H plus I sine H. Yeah, by the way, one linear surjective of K, I think I did check that it should be true that then for bounded H, for bounded elements in H, the cosine and sine should be also in H. I should check that. If it's not true, then you should simply make that an extra assumption. But of course, the cases that we are really interested in is that H is not bounded, but unbounded. Right. Yeah, so this is an element of H, right? E to the G is in H, and this is in H in K. No, in E to H times e to the power HI. Now cosine H can be. Wait a minute. Oh yeah, right. Of course, e to the power HI is an e to the power capital HI. Right. And that is okay, but everything stays inside this big ambient ring, differential ring, and also derivative e to the power f prime, of course f prime e to the power f, is also in K, which is where f was, and e to the power f is. These are just some. Thus, I'm now going to introduce a big extension of K by adjoining all the exponentials e to the power f. It's the ring generated by all these exponentials over K, but as you see, it's enough to adjoin the exponentials of this form. k e to the power h I. And this is simply to set that all the finite sums, k equals 1. Let me write it out. All the sums f1 power v1 I v1 plus power I vn, where f1 to fn are in k, and the v1s to vn are in h. All these finite sums. That's what u is, and it's yeah, and you saw that the derivative of a generator e to the f is also in here, and this means that this is a differential subring. Yeah, all this is inside. All stays inside the big ambient differential ring, but this is too big, and it turns out that u is just big enough for some of our purposes. So it's a differential subring. Is the differential subring of big ambient one. Extending, of course, k. Extending k. And it turns out that is, yeah, and of course, the constants of this ring are just the complex numbers, the element with 0. That's of course then also true for u. And this has a, we'll give this a name. We call this the universal exponential. Well, strictly speaking, the definition is more abstract, but it turns out that this will have exactly the right properties. The universal exponential. Extending. Okay. And yeah, and it turns out this will be worth analyzing with you for various reasons. See. The way I defined u as a subring, it's not perhaps obvious that it is an integral domain. But it is. So right. So we will analyze you in more detail. First of all, for phi and h e to the power I phi is, if you take the germ and you take its absolute value, you know, square root of the real part squared plus the imaginary part squared, then this is always, of course, 1, and it's its logarithmic derivative is, because it's a unit, is I phi prime, and also conversely, everything that has this property, conversely, e to the power hi, exactly the elements in C ambient ring with these properties. U is 1, and U dagger is in I in HI. This is in HI. You can easily check that this is a characterization of e to the power HI, which is what we joined here. Right. Also, if phi here happens to be bounded, yeah, then in fact this is in then e to the power phi I is in k, right? It will then be just a cosine of phi plus I times the sine of phi, and these cosines and sines are in H. So in some sense, these bounded exponents phi here are not interesting because it doesn't give us anything new. And so to get a more useful description, we are going to restrict the exponent phi here to be positive infinite. So for a more useful description, of U, we fix a decomposition of our H into the bounded part and an unbounded part. H is, well, let me call this lambda, capital lambda, plus OH. Into linear subspaces. OH is a linear subspace, R linear subspace of H, but then you can find a complementary one, lambda linear subspaces. Yeah, of course, this doesn't determine lambda uniquely, but it turns out that just fix one, okay, then. So the elements of capital lambda are infinite, not bounded. Unbounded, perhaps, is a better word. And here, this map from lambda to e to the power lambda I is injective, or in fact, it's an isomorphism of groups. Yeah, it's an isomorphism of groups. Here you have the additive group, and here you have a multiplicative group. Multiplicative subgroup, a subgroup of the multiplicative group of units of U. And what we know is that U is, all you need to adjoin is these things, e to the power lambda. Right, because if you have if you go back to, if you adjoin e to the power f, well, one thing is already an H, and let me see. Oh yeah, no. If you write an arbitrary phi as something in lambda plus something in here, and you take e to the power phi, you get e to the power lambda I times e to the power phi I, and the factor e to the power phi I, since phi is bounded, is actually k, so you don't have to worry about it. You just get this, right? And this turns out to be this gives you the structure of a group ring. This and I will explain what I mean by that. This gives you the structure. Okay. Over K with e to the power lambda I as the group. Here is what I mean by that is simply the following fact, namely that the e to the power little lambda I form a basis over K. Opposition. Family e to the power lambda I, little lambda and big lambda, which of course generates this U as a vector space over K. They actually form a basis. The basis K linear space. And well, this is not really hard, but it has useful consequences. It follows that U is an integral domain. Yeah? Therefore, integral domain, let me just say a domain, no zero divisors, except zero itself, and also the units. It follows that the units of this ring are exactly the obvious ones, namely the units of K times anything in e to the power lambda I. These are obviously all units, but there are no other ones. Now, why is this a consequence of this group ring description? Well, you know, if you have a group ring where the group is a torsion-free abelian group, then, well, using an ordering on a torsion-free abelian group, you can show that you get an integral domain. The group ring is an integral domain, and that is why. And in our case, we do have a torsion-free abelian commutative group because lambda, the vector space lambda, is obviously torsion-free, and then its multiplicative copy is of course also torsion-free. Right. So this is turns out to be a useful thing to know. So it has right, but one should not jump to the conclusion that that the fraction field of this integral domain will also be part of, can be formed inside here. That is not the case. I mean, for example, but note cosine x plus I sine plus cosine x plus I cosine x, which is, let's say, e to the power ix plus e to the power minus ix over 2, which is in U, has no inverse. There's no inverse C. Right, so though it is a non-zero element in U and therefore has no zero divisor, you cannot take its inverse. You cannot form the fraction field like this. You can just anyway. This fraction field does exist, of course, abstractly, but it's not too useful, although it plays a role in a few places. Okay, so below, So just to simplify notation, lambda ranges little lambda, so range over big lambda. And when I use and using expressions like summation over all lambda f lambda e to the power lambda I have the obvious meaning in mind, namely that the f lambdas are in K and are non-zero for only finitely many lambdas. It is understood all f lambda are in K, f lambda, but they're only finite. I want this to be effectively a finite sum, so f lambda not zero for only finitely many. Little lambdas. Okay, and now you can quickly characterize those f's in U that are real valued. Yeah, any questions so far? It will turn out that this U is just the right thing to characterize or to solve all linear differential equations over Hardy fields. I guess that is what the main point is, but I will make this more specific. Let's first say what, note F written in the usual way, e to the power lambda I. What does it mean for f to be real valued? Well, it simply means, of course, that f is in here, yeah, f real valued, and so this is equivalent to that f is equal to its let's first say for f new f is this, we have complex conjugate. How do you form the complex conjugate? Well, of course, the complex conjugates of the coefficients, and then the complex conjugate is e to the power minus lambda I, and this is just an L again in U, right? Okay, and now you can see what it means for f to be a real valued. Well, that is of course the same as f equal to its complex conjugate, and so then you have to just compare the coefficients. For this says f lambda, f minus lambda, the coefficients corresponding to minus lambda here should be f lambda r all lambda. So this is and this is also equivalent to, if you you see, so that means that for every lambda, if you combine f lambda and e to the lambda I and f minus lambda e to the power minus lambda I, and you use this relationship between f lambda and f minus lambda, then you can see that this is the same as and you write it all out in terms of sines and cosines, you will see that this is the same as f is element is in this is an element of h plus a finite sum of elements. Where here you have h cosine lambda, sine lambda, and all actually these sums are direct sums. You cannot have any cancellations. So a basis of, right, you might be interested just in the real things in U. That means let's intersect it with this. A basis of as an R linear space, vector space over R is, well, here you basically see what basis you get. One and the cosine lambda and the sine lambda is given by 1 and cosine lambda, sine lambda, for lambda bigger than 0. Yeah, and these are all different things. Right. Okay, so I want to right. So the natural, now we are going to introduce a valuation on U in a very kind of, since U has this nice basis, it is very easy to extend the valuation on K to a valuation on U by just saying the valuation of a sum, like some lambda, the sum over all lambda f lambda e to the power lambda I is simply the minimum of the valuations of the coefficients of lambda, right? So introduce, extend valuation, the natural value, yeah, natural valuation V on K. Let me let gamma be the value group, and of course valuation of, you always adjoin an extra element infinity there, so that the valuation of 0 is infinity. Right, and this is actually this is just the unique valuation that extends the natural valuation on H to evaluation. And yeah, we put here a G for Gaussian, sort of a Gaussian extension, which you also do if you extend the valuation to, for example, a polynomial ring over K. You just take the valuation of the minimum valuation of the coefficients, and so we do the same thing here. G for Gaussian, Vg of some lambda lambda I is the minimum of the lambda. Yeah, in a way it makes kind of sense, right? I mean, if you think of e to the power lambda I as running around the unit circle really quickly, well, they shouldn't really contribute to the valuation. They just stay bounded and also bounded away from 0. And so it should only, so one would only expect the f lambdas to contribute the size of whatever. Right. And so this is a reasonable, and one, yes, and because of this being a basis, one can very quickly show that this satisfies the action for evaluation on a domain, right? And then extend it to the action field. So, don't need to do that. Okay. Aha. Yeah, so now I can make a connection to this corollary, because it turns out that this is just the right valuation to formulate that fact in a useful way for us. Yeah, so this also gives the dominant relation or dominant relation. This is G again on U, just where F Gaussian dominates G. Yeah, of course this is in G and this is, oh yeah, they are both G's. This is slightly unfortunate, but yeah, simply that the Gaussian valuation is greater than the Gaussian valuation of G. Yeah, and of course, likewise with other dominance relation, strict dominance, asymptotic equivalence, and or asymptotic 2, that is what we call this, and this is, I guess, yeah, all these are defined in terms of the valuation in the obvious way. Okay. Yeah, I mean, this business about the universal exponential extension is not really novel. I mean, you can think in another situation, such a universal exponential extension was introduced by in the book by Van der Put and Singer. And I guess we just took it over or adapted it to our situation. Yeah, so note there is one obvious thing about this. If F if F is strictly dominated by 1 in the sense of the Gaussian evaluation, this means of course that the F lambdas, the coefficients, are also are simply infinitesimal. F lambda 1 for all lambda, yeah, that is equivalent. Yeah, this means the Gaussian valuation is strictly positive, so all the F lambdas have ordinary valuation strictly positive, and this implies trivially that F is in the ordinary sense strictly dominated by 1 in the sense of Ci. Well, very much in the beginning of my course, I introduced these dominance relations in very big rings. And of course, this again simply means that Ft goes to 0 as t goes to infinity, right? So, but therefore, right. So now you see that this implies that. But the point is of that theorem there, of that corollary there, is that the converse is also true. Corollary our corollary of Bojanitsan. Tells us we can converse F also true. So the Gaussian strict dominance is a kind of formal way of domination, but this is a purely analytic statement, and that ft goes to 0 as t goes to infinity. It's very nice to know that these things are equivalent. Yeah, so maybe even there's nothing special about 1 here for f in u, and any monomial instead of any non-zero element of k, f, we have let me see, I think this can be we have this, and likewise for the other, and likewise replaced by replaced. Okay. Right, again, the dominance relation here have a purely analytic meaning, and we work in bigger ambient range. Okay. I don't think there's anything too surprising here. I mean, the main thing is factor, basically, is corollary of some result. But we have now put it in a setting that turns out to be really useful for us. Okay. The rest, I have to find my notes now. Right.
May I ask? Should it be different?
I don't think so. No, this is basically more an exercise. I don't think this is. I could be mistaken, but I'm fairly sure that it's not really any big deal. Okay, actually, so far, the strong assumption that K is one and subjective, don't think we used it so far. We replaced this by, I think what is weaker, namely that the cosine and sine of any bounded element of capital H is in capital H. Well, for the Let me see. Ah, yes. So now going back to linear differential operators. Linear differential operators. Over K operates or acts U in a very transparent way. Certainly one of the main attractions of the universe of exponential extension. But for that, I need to introduce a certain twist of A for every lambda. That A lambda is I little lambda is element of big lambda. Oh, I twist it this way. And although what I twist it with will not be in K itself, but in exponential extension, its logarithmic derivative is in K. Logarithmic derivative of lambda I being lambda prime I. And it follows that this is again in K. Easy to check, but then this will also be in again in K delta, not in U delta. Also in U delta equals K delta. And then if I apply A to any element of U, we just apply a lambda to the F lambda. So you see that keep the same e to the lambda i's, but we replace each coefficient function or germ F lambda to A lambda. So that's what I mean by very transparent way. And it means that to solve, again, this is routine check. It's not really, doesn't require much. Just going through the manipulations. So solving AY is 0 in U. If you want to solve in U, it's enough to solve it. To solve these A lambda reduces to all equations. I will K. Well, maybe that's not really a big game, but nevertheless, the main thing is that there is a transparent way of how these operators act on elements of U. And using this, one can deduce with the help of this fact also. That's important. Following which substantiates my earlier assertion that to solve homogeneous linear differential equations over Hardy fields, this U is just exactly what you need. Here's proposition. Yeah, if you look at the curve, yeah, that's A, B, not the trivial operator. And then we know that kernel well, solve AY0, even in this very big ambient ring, C less than infinity I, you have it's a vector space of dimension over R over C, exactly the dimension of the order of A, right? And anyway, but the K-linear space if you only look for solutions in U, it has a basis. Yeah, it's a kind of corollary of solution here, I think. F1 e to the power lambda 1 I up to Fm m e to the power lambda m I F1 non-zero element of K. Right. I mean, there may be several of the lambdas can be equal, right? The number of times that a given lambda appears here is even called the multiplicity of A in respect to lambda. But anyway, several of the lambdas can be equal, but of course, right, for such a basis, I have j with lambda j equals 0, yeah, maybe several fj's and lambda, they form a basis of kernel of A acting just on K itself. Right. And then, and that is the first place where we really need one linear surreactivity assumption of K. If A splits, that's a big if, but if A splits over K, then this dimension M here, the dimension of the of this vector space over K is exactly R. Then M equals order of A. And of course that means that the kernel of A in U is also the kernel of A acting on this bigger ring. If you already have it, if there are already enough solutions in U, then you cannot get any more solutions by going to bigger ring. Yes. Excuse me?
I don't understand why this is a linear vector space. The first one, the canal.
Okay. Yeah, you're right. I C linear. Yeah, of course, it's over the constant field. Yes. Yeah. Everything here is over C. Thanks. Yeah. Right. Thanks. Yeah. I see. I have it incorrect in my notes. Right. And now I want to also say something about the case. My operator is over H. So in order Another corollary, or proposition, whatever you assume. Still, it takes a bit of work to prove these things. So suppose A is now non-zero, but with coefficient of 8. And the R linear space, and now we consider only real solutions. So that, in other words, we take the kernel of A, the solution in U, but only those that are real, as basis. Has a basis that looks has a basis that looks like this: T1 cosine lambda 1, T1 sine lambda 1, Tm Tm cosine lambda m, sine lambda m, and then finally just elements in H itself, Hn, with G1 to Gm in H.
Excuse me.
Yes.
So, sorry for the interruption. It's not for you, Lau. For the online audience, could the person in charge of the camera focus on the right board? But this has just been done, so it's okay. So thank you for the.
Okay.
Sorry.
Yes. G1 to Gm in H. And the lambdas are now positive, real. Positive, and H1 to Hn are negative. Right, so it has a basis like that, and if you want actually the solutions in H itself, then the H1 to Hn here form a basis, for any such basis. H1 the basis. And now I just take the kernel. Since A is now over H, it makes sense to see what are the solutions in H itself, and that is formed just by these things. I next say in my notes, I'm actually a little bit suspicious about if A splits over K, but maybe I meant A splits over H. Then 2m plus n equals the order of A. Maybe I'm not sure what I say here is correct. Okay, but I think the main point here is that that you get a complete description of the solutions of your operator that are in this very big ambient ring, and it's described purely in terms of elements in H, right? The G's and the lambdas and the H's here are all from capital H, so you have a complete description. Actually, now I'm thinking about, wait, this actually does, wait, this has dimension, the order of R. We know that. So if what I'm saying is correct, then 2m plus n has to be equal to the order of R of A. But I'm afraid I forgot to mention just to be on the safe side. Oh, wait a minute. Ah, I see what this is of course, no. Ah, no. Oh yeah, no, this is correct as I stated it. Right. Just wondering what, yeah, I don't think there's anything wrong there. I do want, yeah, okay, but one more thing. If A splits over, yeah, okay, now I remember it. What I wanted to say is actually correct. If A splits over K, will, and if H is big enough, that will happen. Okay, and 2m plus n, which is the dimension of this vector space here, is actually equal to the order of A. And that means that you got all solutions, not just in this intersection, but in fact all the solutions in here. And so all solutions that lie in this ring are actually just linear combinations of things that are purely described in terms of H. Right. And now the thing is, this of course the splitting is a little bit strong assumption, but if your H happens to be D maximal, yeah, then this will happen. In the case. And so right. And so basically we fully understand now how to solve homogeneous linear differential equations over Hardy fields. That's kind of the right. Okay. So that is basically what I wanted to say about this universal exponential extension. And let me again emphasize the role of this corollary of the Boyanin-Sans theorem, which I didn't really make explicit, but believe me, it plays a role in proving these things. Okay, so now I can actually start my last topic for this course, which is again totally different. Right, so all this sketching is really about trying to understand differentially algebraic extensions of Hardy fields, trying to get as complete an overview of differential algebraic Hardy field extension as is possible. And in some sense, we succeed in that. But how about differentially transcendental extensions? So last main topic of my course. Filling gaps in fields. That's the title of preprint, but unfortunately I can't put it as not allowed by my co-authors to archive, because the results depend on a very long set of notes that prove the theorem that I have been talking about earlier. H closed one. And the fact that the notes for that have not yet been fully checked by one of us, one of the three. But again, this has also not been checked by one but a different one. But I know that it is all correct, so I'm myself confident lecturing about it. Right. So the theorem here is that Hardy field. That was one of our conjectures a few years ago, and that AV countable subsets. H such that A is less than B, by which I mean that every element of A is less than every element of B. And so you have your Hardy field, here you have A, and here you have B. And the conclusion here is that there is something in between when you go to then A less than F less than B, or sum F in a bigger Hardy field, sum F in a Hardy field extended. You can always find something, and in a way this is complements what I was talking about earlier. But this really has to deal with F's. The interesting cases is where such an F will have to be necessarily differentially transcendental over H instead of differentially algebraic. Yeah. Okay. So there was one theorem in the literature already about the special case B is empty. Paper by Schöning. Let's see what time. 1970. A Scandinavian journal, 1970. Just a case. That A, B is empty. It's empty. Do I state this correctly? Oh yeah, right. Okay, yes. B is empty. All that means is that if you have a countable subset of a Hardy field, find some Hardy element in a bigger Hardy field that is bigger than everything in A. And well, either there is already an F that in H itself that is bigger than everything in A, or if not, it would mean that A is cofinal. You have a countable cofinal sequence in H, then you have to find some elements in a bigger Hardy field that is bigger than everything in H. And that is what Schöning does. It's I mean, part of our work is really generalizing this construction. Right. So that was definitely a very useful paper. But let me. So I'm just going to say a few generalities and really get to work on next week. So, yeah. So another way of interpreting this theorem is that every maximal Hardy field is what we call eta 1, right? How does calls a linearly ordered set class eta 1 or whatever, class eta 1. If well, if for all countable A less than B as countable subsets of S, there is S in S that A less than S less than. So here the intermediate thing can be found in S itself. And if you look at this, of course, if H is a maximal Hardy field, then this says the F must also be found in this maximal Hardy field because there's no way to extend it further. So theorem is equivalent to every maximal Hardy field in one. Okay. Yeah, I mean, yeah, one of the reasons that eta 1 comes up naturally in model theoretic discussions about ordered sets is that, for example, a real closed field is all of one saturated if and only if it's eta 1. Or yeah. And certainly it's an easy exercise. That's not hard at all because of the quantifier notation. Usually it's stated just for dense linear ordered sets without endpoints. Eta 1, if and only it's all one saturated. Now our maximal Hardy fields are never power one saturated because in a Hardy field you can field of constants is the reals or a subfield of the reals, and so that is which is therefore something that is not all one saturated. The reals is not all one saturated, so a maximal Hardy never be all one saturated. Nevertheless, a corollary of this theorem that, for example, in the setting of just real closed fields, does use all one saturated, but that's not available here. You get that soon, any maximal Hardy fields are back and forth equivalent. Back and forth system. Which is much stronger than saying that they are elementary. Right. Yeah, and so if in particular, this is so strong that if you also assume the continuum hypothesis, they will be isomorphic. Yeah? So isomorphic as Hardy as all the differential fields, isomorphic, assuming continuum hypothesis. Yeah, so of course many people won't like having to think about the continuum hypothesis, and they can just take this as the point. But it's rather remarkable that there is only basically up to isomorphism just one maximal Hardy field. Modulo this very tiny assumption. Right. Okay. Yes. Right. One peculiar thing about the theorem here is that it does not work so far in the setting of analytic Hardy fields. If you assume that H is an analytic Hardy field, then this F, we don't know whether such an F can be found in an analytic Hardy field. The proofs we have do work for C infinity Hardy. So if this is a C infinity Hardy field, we have this, such an F can be found infinity Hardy. But then it is one issue that still been resolved. Right. What else do I want to say? I think I will stop here and really get going next week. Yeah. Oh yeah, and we do have an exercise session at starting at 11, right?